All right, this is AQA A-Level Physics, Paper 3A, that's Practical Skills from the Year of Our Lord 2023. That is Practical Skills. As per usual, I can't show the paper on screen, otherwise AQA will copy strike my channel into the abyss, so we don't want that to happen again, because they almost did in the past. So, 1.1, we have a stroboscope, and we have a duration, and we have a min and a max, and we also have, that's in microseconds, and then we also have the frequency of the flashes in hertz. Okay, so what are we being asked? The duty cycle is T1 over T2, the duration of each flash. So why can't they just say that then? Oh, I see. Okay. Oh, my days. This is confusing. Oh, dearie me. Okay. So we have T1 is that, and then it says T2 is the time from the start of a flash to the start of the next flash. Oh, okay. So that is literally just then T2 is 1 over the frequency. Right. What is the maximum cycle duty of the stroboscope? So we want T1 over T2 to be max. Then we want this to be big, and we want this to be small. The issue is that we don't have T2, we have the frequency, so we know that T2 is equal to 1 over the frequency, so therefore we want T1 times F, because, if they're reciprocals, then this has to be a max to be max. And so that means that we want T1 to be big, and we also want the frequency to be big as well. So there we go. Right, so that makes it a little bit easier. There's less ambiguity there. So if we're just looking for the maximum values, then we can just use 300 and 150. So 300 times 10 to the minus 6 times by 150. So that's, what's that? That's 3 times 10 to the minus 4 times 1.5 times 10 to the 2. So that ends up being 4.5 times 10 to the minus 2. So that's our answer. Weird start. 1.2, we have this ball that is bouncing. Suggest why T1 must be very short in this experiment. So T1, what was T1 again? Oh yeah, that was the duration of the flashes. So we want T1 duration to be short, duration of the flash to be short. And I'm a photographer as well, and I know that when I'm shooting photos or when people are dancing or that kind of thing, if the duration of the flash is too long, then you end up with them being blurred a little bit. So you want the flash to be short, so you just get that very quick image being taken. And so it's the same thing here. So images are not blurred, or we can say they're very defined. And why is that? It means that the position of ball more accurately determined. What have we got here then? The images are used to determine h, the vertical distance from the bottom. So, oh my days, this is a lot going on here. So h, so vertical distance from the bottom of the ball to, I'm just going to say height or max height. Let's say max height or starting height, whatever. And then h is the height at n at some other position. Okay, so the n equals n image is produced, so it's just a specific value of little n, is produced at the instant that the ball hits the floor for the first time. Okay, so we're told that this is the initial velocity. Fine. What are we told then? The n equals big N image is produced at the instant that the ball hits the floor for the first time. Okay, so position at floor for first time, but I'm not going to write that. So what are we being asked then? Okay, so we're drawing a graph, and we've got to figure out what's going to go on the axes, or rather just on the x-axis. So if we have h minus h over n there, what goes on the x-axis in order to make a nice straight line to then get g from? Okay, so if you divide the whole thing by n, therefore you can see that we've gotten rid of an n from both terms on the right. Okay, so then we can say that, well, if this is our y, then this has to be equal to mx plus c, but we want g to be part of our gradient, so we're going to say this is our mx here. So this is our c. Of course, it doesn't have to be going to the origin there like I've drawn it there, but we're not too concerned about that. We're just concerned with gradient. There's a couple of things we can do here, I think. If we just say that this is our x, then that just means that g is going to be our gradient. I think there's nothing wrong with doing that. So n over 2f squared there. That means our gradient is equal to g. There's a couple of things you could do as well. You could say, gn is our gradient and 1 over 2 pi f squared is our x, etc. But this, of course, is the easiest way of going about it. 1.4, we've actually been given some data now. So h is equal to, I'm going to say 1.55 meters with a frequency of 31 hertz. And we're being asked to find out what is the initial velocity. Okay. One thing we can say is that at the floor, we know that little h is equal to 0. And so when that is the case, n is equal to what? So what we need to do then is just count how many times it takes to actually get to the floor, what position it is at the floor. So if it's n equals 0 at the top, then we're going to say, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So I think n is 17. And then, all we have to do is pop that data into our equations. So I'm just going to rearrange for u over f. So u over f is equal to, that's going to be just h over n minus gn over 2f squared. Multiply the whole thing by f, so we end up with hf, and then just one of those f's cancels. So I think u, or u0, is going to be equal to the full height times by the frequency divided by n, and then what do they say, 9.79 times by 17 over 2 lots of the frequency. So let's see what we end up with, shall we? So I end up with 0.14 meters per second, I think. Well, do we need to go? No, I think that's fine. 2 sig figs is fine. Not an easy question, this. What do we have next? Figure 3. So we have N40 to N66. Oh my days. Okay, so it's bouncing a couple of times. Ball makes contact with the floor second and third times. Okay. Determine the horizontal velocity of the ball between the second and third contacts of the ball with the floor. Okay. So are we going to have to infer where the ball is? I think we are we? Or can we just go with those distances there? So, when it's second bounce, it's at 2.2 meters. And then on the third bounce, I think this is probably the trickier one. I think we're probably going to have to infer that it's halfway in between those. Is it cheeky to just go with 3.2? I would be very concerned if they actually said that that wouldn't be allowed there. So I'm going to say that it's traveled 1 meter bang on. And the question is, how long did it take? So going from there all the way up and then down back to here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 positions, I think that's right. If we take the first one as 0, as it were. Oh, we're told from 40 to 60. Yeah, because we're only going from the second to third bounce, actually. So I guess, so 40, 41, 42, 43. So we're actually going from 43 to 66, 65, 64, 63. Are we going to have to go with something like 62.5? If we say 19.5 positions, I wonder if they'll allow that. Let's have a look. If that's the case, then, we want speed equals distance over time. So there's just going to be 1 divided by, I'm going to say 19.5 times by, what is the time? Oh, it's 31 hertz. And so, it's just going to be 1 divided by 31. So in other words, it's going to be 31 divided by 19.5. And so, we're being asked for it in millimeters per second anyway. So I'm going to say that's 1,000. I get 1.5. Actually, it's bang on 1.6000 actually. So there we go, meters per second. So therefore, I'm going to say that's 1,600 millimeters per second. And actually, looking at the mark scheme, that's bang on in between their ranges. But hey, it worked out in the end. So I guess the range allows you to go from 19 to 20. Oh, dearie me, I do not like this question one bit. Very ambiguous. Determine the time between the second and third contact. But didn't we have to just do that? Determine the time. So time between bounces would be just, I'm going to say time period is equal to 1 over the frequency. So therefore, the total time is equal to, just 19.5 of these divided by 31. 0.63 seconds. Can we change question, please? Yes, thank you. Finally, a bit of electricity, hopefully less ambiguity here, but I don't know. Sure, they found some way to ruin this too. So we're not going down to 0, so I guess that's important. We are going down to 0 there, and that goes up to 12. But we're starting at 0.2 there, aren't we? Going up to 2. So graph is doing something like this. Okay, so the current in I was measured across L, increased the state rate. These data were obtained using a sensor. The logger recorded data at a rate of 2.5 hertz. So we need to know the time period then, don't we? So t is equal to 1 divided by 2.5. So that's going to be equal to 0.4 seconds. That's going to be helpful. Or actually, I guess we didn't need that. We could have just said that this is seconds to the -1 because we are looking for volts per second. Okay, the rate increase of the voltage. Okay, so the voltage is increasing by the same amount every time. Yes, that does make sense. Okay, so we might as well go for something at the end because that'll be a little bit more accurate, one would have thought. Or can we go for one that's a nice number, the one that's on a line? Can't really see one that's on a line, to be perfectly honest. I guess there is one there, actually. There's one bang on. Let's go with V is equal to, what's that, 5.8 volts. Okay, and the number of readings that it took to get to that point is, actually, I guess we're going from 0.8 to 5.8 volts. So that's 5 volts, because there's no reading on 0 volts, is there? So going up 5 volts, that took, starting at 0 and going 0, 1, 2, 3, 4, 5, 6, 7, 8. So it took 8 readings to get to that point. And so, therefore, I'm going to say, yeah, let's do that. Therefore, V over T, because that's what we're looking for, is equal to that 5 volts divided by the total time. So that's 8 times 0.4. And that gives me 1.56 volts per second. There we go. There is a little bit of tolerance there as well, though. 2.2, 2 advantages of using a data logger for this experiment. Well, we're not going to say that it's a higher resolution because it's not really, is it? So I guess we're talking about like reducing uncertainties and errors and things like that. So we could say reduces random error due to reading voltmeter at correct times, and also we could say time interval too short for human, because good luck making a reading every 0.4 seconds. You get the idea. So we could say collected at a higher rate, or collected at a faster rate. Okay, what else could we say? I guess we could say that, you know, we are reading V and I. V and I recorded at the same time or simultaneously. Very difficult with doing that as a human, isn't it? Doing 2 readings at exactly the same time. I guess we could say, you know, it automatically produces a graph. So automatically produces graph, and that's going to be accurate as well. Yeah, there we go. That'll do. 2.3. What do we have? We have X here. Oh man, these are complicated circuits. I don't know why I've done the voltmeter in blue, but whatever. I guess I better be consistent. I actually like doing that, so it makes it a little bit easier, come to think about it, to see what the circuit is instead of the voltmeter sort of distracting the eye, as it were. So it's easy to see the left circuit, series, right circuit, definitely in parallel. But it's only in parallel with this part of the resistor, and we're going to have to consider that in a bit. Guaranteed. So we actually are essentially splitting this resistor into 2. So we have the parallel bit is in series with the left half of the resistor X. Okay, so the max resistance is 14.9 ohms. We're told that when X is set to a maximum resistance at this point, so resistance of L is 2.3 ohms. Okay, and then X is used as a potential divider. Right. What are we being asked then? Discuss. Oh, that never bodes well. Discuss whether either circuit can produce all the data shown in figure 4. Right, so we need to go. So we need an I min of 0.36 amps. We need an I max of, what's that, 1.94 amps. We need a V min of 0.8 volts. And we need a V max. I'm just looking at the graph here, just the top and bottom points. And we need a V max of, what's that, 11 point, let's err on the side of caution, let's say 11.6 volts. Okay, so that's what we need. Which circuit can produce this data? Okay, so let's first of all look at when R is at a max here. So that means that the contact would be there, of course. We have that. Okay, so if that's the case, then of course we're going to have to employ V equals IR, aren't we? And also our potential divider equation as well. So here we go. Let's have a look at this then. So we can say that, tell you what, let's just do V equals IR for the total first and then find out the current, because we've got to find out the current anyway, so we might as well. So V equals IR, so I is equal to V over R. And so that's equal to the whole 12 volts divided by, what's that? 14.9 plus 2.3. So that's going to be 17.2. And that gives us I'm just going to say 0.7 amps. Oh, okay. So we already have an issue, don't we? And that is that we can't go down to the minimum current of 0.36 amps. So that's a bit of a problem. So this is at a maximum resistance as well. So therefore, it doesn't look like this is going to work. Cannot reach minimum current of 0.36 amps. Yeah, and so also, well, let's just, why not? Let's figure out what the PD is across the bulb, because that's, of course, what we're concerned with. So V equals IR for the bulb, so for L, and so that's going to be 0.36. So times by the resistance of 2.3, that gives us 0.83 volts. And so, well, yeah, that's an issue as well, because that is when the PD is at a minimum. And so we can increase the PD across the bulb, because we can decrease the PD across X, but yeah, we can't make it any lower. So same for V min. So hopefully circuit 2 is going to be the one that actually does do this. So let's have a look. Let's have a think about when we actually have the contact going all the way to here. Now, it's a little bit hard to see because it might be worth redrawing this. When we actually put the contact there, what we have is essentially we're shorting the bulb. So when the current gets to this point here, it's not then going to go down here, because that's resistance is just going to go straight through the wire there. So when we can say contact is at right, V across the bulb is equal to 0 volts. When the contact is to the left, well, that means that the PD across X is going to be 12 volts, and also that's going to be the case for the bulb as well. We have a full parallel circuit. There's nothing in series, as it were, and so we can say VL equals 12 volts. So yes, we can say that it does satisfy all of the voltage readings as well. I think that's probably it, because we can't really tell what's going on current-wise with the bulb, because we're only told what the resistance is at this point here. So we don't know what the resistance of the bulb is going to be. No, we can't know that. So I think that's probably okay. So assuming that it's all right, yes, circuit 2 is going to be able to do that. 2.4, we have a table. We're just being asked to complete it. We're literally just multiplying values. So we're going to say 5.17 times 1.32, because of course P is equal to VI. So I guess they're just testing to see whether or not we can actually record value to right number of sig figs. So that's going to be 6.82 to 3 sig figs. And then we have, so we have, it's points plotted on that. So we're going to say 9.58 times by what is the current at 9.58 volts, going back to pages and pages. 9.58 volts, that's that one there. There we go. And I can see that is 1.7, what am I going to say? 1.77. I'm going to say 1.77 amps. Let's go with that. And what's that going to give us? That gives us 16.9 but we only want 3 sig figs. That's interesting. They've given the data to... Oh, no, I guess that makes sense. So we're going to say 17.0 watts. 2.5, we're being asked to plot a graph of P against V. Hopefully we should just see a nice sort of curve going up like that. But the point is that we have to make our y-axis as well. What's the maximum current? It is 22. So how many boxes do we have to play with? 1, 2, 3, 4, 5, 6. I guess it makes sense for us to go up in 5s then, doesn't it? Don't try and be clever with your axes. Never, ever, 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 ever try to go up in 3s or 4s or 6s or 7s or 8s or 9s, etc. You can't do it. You can't plot points if you use those numbers on your axes. 2.6 L is then connected to a 12-watt power supply. Okay. Second lamp is now connected in series with L. Determine the percentage of P that is dissipated in this circuit. Fine, so we're going from just that to this, and 12-volt power supply. So if it's a 12-volt power supply, then, well, let's just use our graph. So going to 12 volts here, we end up with, or we should end up with something like a power of something like 24, maybe slightly under. So we're going to say 23.8 watts. But here now we're going to have 6 volts and 6 volts because that 12 volts is being shared equally. So then going to 6 volts, what do we end up with? We're going to end up with something like 8.5 watts. But remember, that is per bulb. And so the power here would be 8.5 times 2. There is a little bit of tolerance here, of course. And so that's going to give us 17 watts. Okay, so what are we just being asked? Just the percentage of PT that is dissipated in the circuit. Okay, so it's going to be less in the second circuit altogether. We can see that, can't we? And so we're just going to say 17 divided by 23.8 times by 100, or in other words, 1,700 divided by 23.8, and that gives us 71.4%. Weird question to end on there. This is a terrible paper. My word, I hate it. Okay, we have a Helmholtz coil or whatever, and we have a field that's going like that. We're looking through it sideways in Q, or in the side view, sorry, 7B rather. Discuss whether a search coil is a suitable sensor to detect BH. That's an interesting one. The issue is with a search coil is that we must have a search coil. You've seen them. It's just something like that. Maybe it's not a little stick. You stick it in between, and then it's got wires that go to a data logger. So we must have a PD or an EMF rather induced in the coil. What's the issue with that, I hear you ask? Well, just like anything with induction transformers and that kind of thing, if we just have a constant magnetic field being produced by the coil, then of course we're not going to be able to have anything induced. As constant, or as BH is constant, no EMF induced in coil. So it is very unsuitable. It won't measure anything. Okay, but then turning it through 25 degrees, determine the percentage change in BH produced by this rotation of the coil. Ooh, interesting. Okay. So I guess, it's just going to be 25% percentage change. So we're going from 100% down to what? Well, it's just going to be cos 25, isn't it? What is cos 25? Cos 25 is equal to 0.91, let's say. And so therefore it's going from 1 down to 0.91. So therefore the difference in BH is going to be just 9%. Guess we probably should do that to 2 sig figs. Fine. So I'm going to say that is 0.906. And so therefore we're going from 100% down to 90.6%. So therefore the difference in BH is going to be equal to 9.4%. Okay, we have a protractor, blah, blah, blah. Estimate the percentage uncertainty in this result. Ooh. Okay, so again, a little bit of ambiguity. I'm going to say the uncertainty is equal to 1 degree. Now, It's basically chance as to whether AQA, it depends what mood they're in, whether they think the uncertainty is half the resolution or actually the resolution. I would say that with a piece of measuring equipment like this, it should be just 1 degree, it should just be the resolution, not half the resolution. So I'm going to stick with that. If you want to go with half the resolution, that's fine. I don't care. I've talked with AQA about this, with the practical leaders, and they've said, we don't know, to be honest. Either is fine. They don't know what they're doing. They can't decide one way or another. And so there is always ambiguity with uncertainties, but they take it to the extreme. So therefore I'm going to say the percentage uncertainty is equal to 1 divided by, 25? 25 and then times that by 100. So I'm going to say 100 divided by 25, so that is going to be 4%. In a Mars scheme, they say, the Mars scheme. Between two measurements, blah, 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 blah. That's not true, because lining something up on a mark is not the same thing as measuring in between two marks on your protractor, etc., etc. So the Mars scheme really should, it's got a whole mess there. What it should say is literally just absolute uncertainty could be half a degree or 1 degree. That's it. Like, they're trying to just talk about absolute rambling. Okay, we are going between two coils now. So we have, I see. So we're going from maximum current to minimum current, and then the opposite there. Right. So what are we being asked? The sensor is moved along PR until the value of BH is halved. The distance from Q to the sensor is that. So X 0.5. Why didn't they just say X half? So it's measured at Q, fine, and then it's moved till it's halved. And so we're just looking for the distance going from, what's that? Oh my days, I hate this paper. 0.6, what's that? 6.5? Yeah, that's the peak. And then that's going down to, well, that's got to go to half, isn't it? And so we're talking 0.332, let's say, because you can't really go to the full sig fig there. So 0.332, I'm going to say that is, I can't really go to that 0.332 to be honest either, but hey, we'll give it a go. So I'm going to have to zoom in here. So I'm going to say that's bang on that line there. So I'm going to say 52 millimeters. Let's go with that. So that's our X 0.5, and then R is, we're going from one to the other. So I'm going to say from 0 to, so the peak of the other one is going to be 60, let's say 67, I'd say. Let's go with 68. There we go. So therefore X over R is going to be that 52 divided by 68. My days, this paper. This is the worst paper 3 I've ever seen. This is shocking. So I end up with 0.76. It's just random, just bizarre. 3.5, they're both switched on now. We have a constant maximum value. Okay, so the graph would actually look something like this instead, because we've got both combining in the middle there. That's nifty. Deduce in millitesla the value of BH in this region. Well, so it's just going to be just the sum of both of those fields. So I guess we could just take the bit in the middle, where they both cross. We'll just take that bit there and then double it. That's fine, isn't it? Because we know it's just going to be constant all the way across. It's just superposition in a way. And so I'm going to say 2 times, so B total is equal to 2 times 0.475, I think. But that is millitesla, isn't it? So I'm going to say that is, so 2 times that's just going to be 95, so 0.95 millitesla. I think that's all we're looking for, isn't it? Yeah, that's all we want. Oh my days, when will this be over? Thank goodness it's only half a paper, eh? State 2 characteristics of the magnetic field lines in this region. Well, if it's a uniform field, they are parallel. And also, I guess we could say, if it's a uniform field, that's the whole point, is that they're just like electric field lines, gravitational field lines. Don't really see it with gravity though, but electric field lines, they're parallel and equally spaced, or evenly spaced. 3.7, one of the coils is reversed and the magnitudes are still that, but just one is the opposite direction. Sketch a graph to show how BH varies between X and R. Oh my days. Okay, so we know that it's going to go below 0 because the field has to be in the opposite direction, doesn't it? So whereas to begin with both of them going in the same direction, basically one of these is going to be flipped, isn't it? So we know we're going to end up with 0 in the middle, aren't we? And so, well, what's it going to look like? Is it going to look something like this? So basically, if I'm not going to be calculating any values here, so I think that's, vaguely okay. Maybe I have curved a little bit too much. Maybe it's not going to be like that. But tell you what, I'm going to play it safe. I'm just going to go sort of like that. Play both sides there. Include numerical values that correspond. Oh gosh, you do actually have to have numerical values. Okay, so we have x equals 0 here. We have x equals r here. And then, of course, here we're going to have x equals. But then we need to have values there as well. Okay, so on the left-hand side here, we're going to have that 0. So from the first call, we're going to have 0.58 millitesla take away because it would be in the opposite direction. So that'd be 0.15. And so we should end up with 0.43 millitesla. And of course, that's going to be the same there as well. So that's what I think it's going to be, 0.43 millitesla there. And then minus 0.43 millitesla there. There we go. Gosh, yes. I mean, people complained about the 2023 papers. Paper 1 and paper 2, while they had their moments, they weren't horrific. This paper is horrific. This is awful. But if you found this a little bit helpful, then leave a like and leave a comment down below as well. Don't forget to check out my practical skills video for paper 3A, which goes through the kind of skills that you need to have for this paper. And I'll see you in the next video.